All right, and this is not really a proponent presentation. This is something we did for the level 2, and it was in many ways simplified. Turns out it works really nicely, as we'll see later. But it's the idea of trying to come up with GMPs that were applicable at this distance range that we're talking about 200, 300 kilometers, which come from Cerro Piero and other sources. And actually, taking away the resource expert or proponent expert hat and getting into the hat of the member of the source characterization team for Palo Verde, I want to emphasize that all the results that Melanie has shown are preliminary. And what I think the lesson we should get from that is that both the local sources, which are likely normal but might not be all normal, and the distant sources from Cerro Piero and from San Andreas are important. So I think the project needs to keep focus on both sides of the issue. Cannot neglect one at the expense of the other, because the relative importance of the, right now they show fairly equal, I would say, in terms of importance, and the relative importance may change one way or the other. Okay. Now let's get to results. Again, data on regional queue. Kevin showed you a lot of that. I'm not going to repeat that, but I'm going to just have one zoomed in map that kind of shows things in what I see it a little bit more clear way. Then I'll show you how we treated path effects in the level 2 study, which is, again, a simplified way of doing, but it shows what one can do with this information. Comparison to NGA West 2, and then responses to the specific TI team questions. Okay, so this is the map from the Phillips et al. Paper that Kevin showed you, and I'm showing the frequency bands. I think it's easier to interpret Q and just in terms of the frequency bands instead of Q and eta, because again, we're not so good at doing math in our heads. Now, if you zoom in, and this is a kind of a crude zoom, well, it's almost unreal. There's nothing there to see much. But in any case, in my original version of the thing, but what I was going to, or what my original slide showed, is that you do have a higher Q around the basin and range region. You see it more in the high frequency area, high frequency band, and this is the site, approximate location is this star. And you generally see that coastal California has a sharper, darker red than the basin and range. So it's higher Q. How much higher is hard to see from these numbers, but we have all the information from these figures, but we have all the information that will allow us to perform that calculation. And again, the paths from, again, getting oriented here, actually I'll look this way, and maybe I'll get oriented here and show you. Something like Cerro Piero will be, okay. Should get used to the idea that this projector never projects very well. Okay, Cerro Piero will be something like, it's hard to see, around this way, more or less, this path, and the San Andreas will be something like this. Okay, enough of that. So again, the idea, the general lesson from there is it's a higher Q, less attenuation, at least as a rough initial estimate for this path than for a typical California path. Of course, as I'll get to later, the definition of a typical California path is a little tricky because all you care about is the long paths that were used to calibrate the long distance portion of the model. You don't care about the many short paths that were used for other things. Okay, this is what we had at the time, NGA West equations. Here we have the results for 7.5 1 Hertz. And as you see, two of the equations had inelastic attenuation terms. Atkinson-Bohr, or Bohr-Atkinson, and Chu-Young's had inelastic attenuation terms, gamma terms. And you see that they do have similar predictions over the entire range of distances. And what we care about is 200 to 300 kilometers, but I showed it up to 1,000, kind of Eastern US bias. You also see that the others are off by roughly a factor of 2, maybe more, in this distance range of interest. We look at another case, still 7.5 PGA, very much the same kind of behavior. Now, so I'm going to show you what we did to make a workable model out of this that we had. So first thing we did was focusing now on the solid lines. Is we see again the two of the models do a decent job, or a good job, at all distances. The others two don't. And we chose the Chou-Youngs as the preferred one of the two, because the main reason is because you have a magnitude dependent gamma, and you have a truncation. Again, truncated regression is close to my heart as a topic. So I like the idea. So what I did for the others, for the Abrahamson and Silva, and for the Campbell and Bosornia, I took them at their word and assumed that up to 200 kilometers they were all right. And then at 200, I spliced the Chou-Young shape. This is what you get. Then the solid lines is what you get with the base case Q model that were used by Chou-Youngs. Oh, and by the way, the Bohr-Atkinson I left alone in that case. Now for the second step, I said, well, remember from the Phillips et al. That Q is somewhat higher for this region, less attenuation. So I modified the gamma terms in these attenuation equations proportional. So I assume 50% higher net Q over the entire path, which implies the gamma term goes down by 1/3.
So Gabe, is that the Salton Trough path or the Sierra Prieto path?
At this stage, it's very qualitative. At this stage, it was this was before we had this was before we had the aggregation results, before we had any of these things. So it was a very rough estimate. Again, when you say 50% higher, then clearly there's no precision there. And you see the effect, at least if the change in Q is on the order of 50%, the effect is not very large. It's much smaller than the model-to-model variation that you had at 200 kilometers, but you see some difference. Actually, at PGA, you see less of a difference because the PGA is probably controlled by long periods anyway. At some other frequencies, some intermediate frequencies, you do see more of an effect, but still, that effect is not very large, smaller than the model-to-model variation that you have at 200 kilometers. So we did that for all frequencies, and we considered all these 8 models in the hazard calculations. Next question was, how do they compare to NGA West 2? And here are the results for, again, 7.5 PGA. Remarkable. They match very nicely. So the NGA West 2, again, those of you in the rear won't be able to read any of the legends, because now we have a lot more models. We have 5 more models, and they are ASK, BSSA, CB, CY, and IDRIS. Now we have the 5 shown as dots. But again, in general, you see that the dots superimpose nicely with what we had before. Another case, magnitude 5.5, again, not very important at this distance, but I still plot. And again, in most situations, you match well. There's sometimes one stray model from the original attenuation equation that is higher, but in general, there's a fairly good match. 7.5, 10 hertz, again, very good agreement. And not only in terms of the shape, general shape, but the spread is very similar. 5.5, 10 hertz, same lesson. And most of the other cases, 7.5, 1 hertz, again, similar, more spread here, because again, this is one case where it's really the 1 hertz energy that matters, not the, not the integrated form, which is what you are seeing at PGA and at all the higher frequency, not the integration over the entire spectrum. You see a little more of a spread, but in general, there's a good match. 7.5, 0.1, there's the IDRIS model does something funny here, but it does it beyond 300 kilometers. And this one doesn't matter. 5.5, 0.1 hertz, you don't care. And even there is not too bad. So in general, I was surprised to see how well they match. One thing I need to confirm is this is some code that I got from Linda, that she got from Nick. I think this is done with the regional, with the composite Q model. That's my suspicion. And I think that needs to be confirmed, because again, there are alternative Q, in some of the NGA West 2, there are alternative Q models for different regions, Japan and so on, that were discussed earlier. I think these are with the composite Q model.
I'm not sure what you mean by composite. Q
Well,
model.
the global, okay. Global Q model
Okay.
without the regional adjustment. That's my feeling, needs to be confirmed. Now, in response to the TI team questions, again, what's the regional difference? At this stage, again, I can only answer that qualitatively. That is not for a specific path, as Norm was asking. But what I assumed there was roughly 50% higher Q, which doesn't make a huge difference compared to the other uncertainties we have there. But if it's a double in Q, then that will make more of a difference, etc. The other issue is that the way I corrected the gammas probably overestimates the effect. Because again, always when you, let's see, yeah, you put more, well, it works in the other, yeah, I think you overestimate the effect because the speckle shape may shift and so on. So you may be, higher Q probably doesn't matter too much. Lower Q, you would be overestimating the effect. Is this difference consistent with the ground motion data residual? Again, the residuals are not available, but that should be done. That's one, again, there's two pieces of data that need to be used for this work, it seems to me. One is what Kevin showed you earlier, and those maps, a regionalization of Q, and the actual recordings and the residuals. So that needs to be done. But again, it wasn't available at this stage. What is the impact of the Q difference at a distance 250, 350 kilometers? Kevin showed you some numbers. The way I see it, you should do it is, again, quantify the difference it's not really in Q, the difference in 1 over Q over the specific paths of interest using the gridded data. Then quantify the effect using an approach similar to what people use for VS kappa corrections. Again, do IRVT to get a Fourier amplitude, adjust the Fourier amplitude, convert back to spectra, and check there. The one complication there, as I mentioned earlier, is the reference path for the NGA equations is a little difficult to define. I think unless you start looking, I don't know exactly, for example, what data you guys used for defining your elastic attenuation model. Was it California data or was it data from where? Or which paths are those that were used to constrain the long distance behavior?
Which version? Which model?
Oh, let's say
The new
two,
one?
the new one.
The new one, we used data from California. We looked at the individual earthquakes that we could regress everywhere.
Okay, so we know, we know
So
what
we
those
know
paths
which
were.
ones, so the base model is based primarily on California data.
Okay, but
with-
different California paths going from the Sierras and,
All of California.
okay, so, but
It's
it'll have
not
to be done.
specific,
Yeah,
it's not
it'll have-
specific to a path that goes through this area. no.
Exactly, so it'll have to be done event by event.
It was done event by event, yeah.
And getting the reference 1 over Q, path 1 over Q will have to be done event by event, I think, I'm afraid.
Well, the final model doesn't have event-specific Qs in it, or gamma terms.
Yeah, but for us to define a reference 1 over Q, or the average 1 over Q over the path, we may have to at least look at your map of paths and then decide on that. So it's not straightforward, is what I'm trying to say.
But we don't, there isn't really a global Q model, at least in, we had the full data, the global data set, we pulled out areas, like Japan is different.
Yes.
And maybe Taiwan is a different rate or whatever it is, and everything else that was left, not different from California,
Yeah,
that's the default model.
okay.
So California is really what you should be using as your reference. That's going to be by far the bulk of the
Okay,
data.
okay. But it's still not straightforward because again, you have to see if it's north or south and what kind of paths do they cross the valleys and so on. So it's not so straightforward to define what is, because I talk about, again, difference. And the difference
the
implies
difference.
there has to be a reference, and the reference can be calculated, but it's not straightforward, or it may not be straightforward.
But when you show that one comparison, saying taking the NJUS2 model, which was essentially a California model, and that is now similar to your
Yeah.
Q-adjusted
Yeah.
older models, right?
Correct. So yeah, it may be that this step is not needed, but if you were going to do it quantitatively, you have to go through these
The
steps
steps,
which
yeah.
are not so straightforward. But it may be, based on my comparison, that is not needed. Okay, and present comparisons again with the, sorry. 2010, it's not 2000, it's 2012, okay. In any case, we presented the comparison, they match surprisingly well, and I was really very surprised that they match so nicely there, showing that there's some consistency in between what we did and what's coming out of the new equation, the new NGA West. And that's all I have.
That still seems not the expected result. If we had taken the new models have a better Q term in them, right? Much
Yes,
better.
much better.
But they're now consistent from the California model to what you adjusted to Arizona, but shouldn't it still become flatter in Arizona than these NJ West 2 models?
Well, yes. Yes, but again, if you go back to this figure, and similar figures that I did not include, it looks like that the effective Q here is not very large. It's much smaller than the effect, than the expert-to-expert difference.
This is Robin McGuire. The thing is, Gabriel hasn't shown any Arizona data because we don't have any
We don't have
at
any.
this point. So
Right.
this is just speculation,
Okay.
and the NGA2 agrees with the speculations.
That's good. That's
There's
a good
no
way to
data
put
here.
it.
There's no truth
That's a
here.
good way to put it. It
So-
agrees with that, with a very simple model that we use for the level 2.
Yeah, the thing, let me continue. The thing that I hope is that the Q model will be explicit in these ground motions that come out of this project so that we can change them, or that they can be modified explicitly for Arizona.
Well, that would be nice,
Yeah.
because that way you can also tailor it for different sources,
Yes.
if it's different
If
enough.
if it's
The
built
only-
into these complicated equations, that's going to be very difficult.
The only way we were going to do it is to change the linear distance term.
The gamma.
That's it.
A linear distance term.
Well, the gamma term.
So we have our normal log distance, and then on top of it, there's a linear term, and we're just going to adjust that to match the data and be consistent with what the Q says it should be. Hopefully, those are going to
Okay,
be
well,
consistent.
Then an explicit explanation of what that adjustment is and how we would do it for different Qs would be useful, very useful. So that if we have some path that has a special Q, we can account
You would
for
need
it.
to adjust it there, okay. Bob, are you turning your gammas into Q numbers or not? I mean, do you have a translation of what the gamma effect is with relative to the Q model?
No, we haven't done it.
That way, okay.
No, we just,
As a
Because
rough
we're-
approximation for anything other than PGA is to assume that it's proportional to 1 over Q.
but we have magnitude dependence in there.
You have magnitude
Yeah.
dependence, which will shift. Again, if you do it right, you really have to go through the steps,
Because
the IRBT and all that.
Because our magnitude dependence varies with period. It varies, we found it's not a very clean, where you can just shift it up and down. The magnitude variation with period in response spectra space is a little complicated
Especially for
Okay.
PGA, but I'm sure for all of them too.
for all.
But we need to provide it in a form that they can convert Q to gamma, whatever we're going to
Mhm.
say, so that they can easily adjust the model, and we probably have to build it in there. The coefficient on gamma is some Q relative to the California Q model or something like that, right?
Yeah, if the effect is large enough, yes.
Okay. If it's too small enough, we'll just smooth through it.
Yeah.
Okay.
Any other questions?